Well, hello, my name is Chris Barkin. I want to welcome all of you to the virtual William W. Hay Railroad Engineering Seminar. Before I introduce our speaker, I'd like to remind listeners that you can ask questions using the question box on the side of your screen. One of the moderators of this seminar will read them to our speaker at an appropriate time. The William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us at RailTech, we thank AAR, BNSF, CN, Hanson Professional Services, and Union Pacific for their ongoing support of RailTech and activities such as this. It's greatly appreciated by those of us here on campus, as well as those participating via the internet. I also want to welcome the more than 150 people who registered for this seminar. They hail from 14 different nations on 5 different continents, so this is truly a seminar with international interest. Further underscored by the fact that our speaker is joining us today from his home north of Stockholm. The list of attendees today includes freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, research organizations, technology developers and suppliers, and others. We're very pleased that you can join us for what I know is going to be a very informative presentation. Those of you who wish to receive PDHs for your participation, please send us an email at heyseminar@illinois.edu with your information as described in the email announcement for this seminar. Our final Hay seminar for the spring semester will be in 2 weeks, and it will feature Dr. Sam Alibrahim, who is with the FRA, and will be discussing some of their latest research on positive train control technology. Please visit our website for more information about that. Wheel and rail damage maintenance is a major expense for railways. Ideally, railroads could optimize this expense by conducting it as often as needed to assure its safety, but not so often as to be unnecessary. The KTH Railway Group has conducted extensive research developing simulation tools to accurately predict wear and rolling contact fatigue on wheels and rails. As such, this work can be used to develop digital twins to predict maintenance requirements specific to particular train operation. Our speaker today will present examples of how simulations are being used to optimize rail grinding intervals and predict wheel life, thereby enabling accurate forecasting of wheel turning requirements. He'll also describe some examples of how machine learning algorithms can be used to detect vehicle component failures and to monitor and identify various track and rail related problems. Sebastian Stichel completed his BS and MS in mechanical engineering at the Technische Universität. I'm sure I kind of destroyed the name of that one, but better known as TU Berlin. He then went on to complete his PhD in vehicle dynamics, also at TU Berlin. From 2000 to 2010, Dr. Stichel was employed by Bombardier Transportation in Sweden, and in 2003, he headed a vehicle dynamics department with employees in Sweden, Germany, the UK, and France. Dr. Stichel joined the KTH faculty as a professor in 2010, and in 2011, he was named director of the KTH Railway Group. 2013 to 2019, he was vice head and then head of the Department of Aeronautical and Vehicle Engineering, and since 2020 has been vice head of the Department of Engineering Mechanics. He's also served outside the university since 2017 as vice chair academia of the European Rail Research Advisory Council, and was the Shift to Rail Scientific Committee from 2016 to 2018. He's been a board member of Swede Train, the Swedish Association of Railway Industries, since 2019. His primary expertise is in dynamic vehicle track interaction, mainly using multi-body simulation. His current research interests are focused on improved ride comfort and reduced wheel and track damage. He's also involved in research on active suspension and the dynamic interaction between pantograph and catenary. I would also mention that Dr. Stichel is one of the architects of the academic partnership between KTH and the University of Illinois in railway engineering that has been developed jointly over the past decade. He first helped to develop the structure of the joint program and now serves as the instructor for one of the classes available to Illinois students, as well as, of course, KTH students on rail vehicle dynamics. I'm very pleased to introduce my friend and colleague, Professor Sebastian Stichel, who will present his seminar entitled Wheel and Rail Maintenance Planning with Support of Digital Twins. Dr. Stichel.
Thank you very much, Chris, for this extensive and nice introduction. And above all, thank you very much for inviting me to give this seminar here this evening. It's a real pleasure to participate. I participated once earlier when I visited you for 4 weeks, but that was 8 years ago in 2013. So it's really nice to be on the seminar again, and welcome everyone today here to this seminar. Chris already introduced the topic. I will talk about how wheel and rail maintenance planning can be supported by using digital twins. And the work that I will present is, of course, not only done by me. It is actually even mainly done by many of the co-workers, PhD students, postdocs, and 3 of them which are at the moment working in our research group I mentioned here as co-authors of the presentation. Since all of you might not know where I'm from, a very short introduction here. I'm from the Royal Institute of Technology in Stockholm, Sweden, which is the largest Swedish technical university. We have 5 campuses in the Stockholm region. And I'm also, as Chris introduced, director of the KTH Railway Group, which is a multidisciplinary railway research center at our university. We conduct research and actually also education in many different fields of railway engineering. We are in civil, electrical, and mechanical engineering, and you can see just some examples. We deal with train traffic planning, scheduling, as you can see here, traffic and logistics, with signaling, tribology issues. We have quite a large group working on railway bridges, also quite a big group in electrical engineering working on power supply and electrical propulsion systems. And then we have the group where I am from, the rail vehicle group, that mainly works on vehicle track interaction. And on the next slide, you get a short impression on what the research focus in our group is. As said, it's mainly on the dynamic vehicle track interaction with topics like ride comfort, contact mechanics, damage prediction, active suspension, tilting trains, crosswind stability, and condition monitoring. But we also have some projects on energy usage and environmental impact of railways, lightweight structures, and vehicle catenary interaction. And finally, before really starting with the topic today, I don't need to say so much anymore because, Chris, you mentioned it already. We actually have a quite close cooperation between the KTH Railway Group and the RailTech Center. And as you said, it goes quite many years back. And since 2018, we have it officially our joint master program in railway engineering, where students in parallel start at UIUC and in Illinois and at KTH. Okay, but now to the topic of today. What will I be talking about? After a very short introduction, I will mainly try to explain to you what we are doing by examples. I will not talk so much about theory, but by some examples of what we are doing, hopefully give you an impression on what it is and how it could be used. I will talk about how our calculations could be used for optimizing grinding intervals, for wheel life prediction, shortly a bit on our activities on machine learning, which are much newer than the other activities, and then shortly summarizing it. As a background, Chris also mentioned it very shortly. Rail damage, rail wear, and RCF, for example, according to information from Trafikverket, which is the infrastructure owner in Sweden, accounts for about 40% of the maintenance and renewal costs in the Swedish network. And also wheel maintenance and renewal is a significant part of the operational costs for the vehicle side. So if you can save some money there, you can save a lot for the total operation cost of a railway system. Another issue is that wear and rolling contact fatigue are interlinked. You can't really look at one of the phenomena isolated. You always have to look at them in combination. A very obvious reason is that initiated cracks can be worn away if you have wear, which you always have between wheel and rail. So actually a certain amount of wear can be beneficial to not have too fast crack growth in your system. And third bullet point here is that also maintenance activities influence the wheel-rail dynamic interaction. When you reprofile the wheels or when you grind the rails, then you change the geometric interaction between the two contact partners, and that also changes the dynamic performance of the vehicle on the track. So it's a quite complex system that needs a lot of detailed attention if you really want to model it in a good way and get good predictions of the system behavior. In that aspect, it is also, as I said, a system tool, the wheel rail damage prediction. What would we like to achieve? Yeah, like most people would like to achieve higher infrastructure availability, reduce track maintenance, reduce costs due to delays, lower operating costs, and the same on the vehicle side, reduced vehicle maintenance, higher vehicle availability, but also better ride comfort and less running instability, this hunting motion. And to build a digital twin of the system to predict wheel or rail damage, you need quite a lot of different bricks here, and that I have indicated a little bit on the left side. Firstly, of course, you need a good multi-body simulation models that really represent reality. You have to deal quite a lot with contact mechanics. You need to post-process the outputs from the dynamic simulation, so you need the damage models, how to come from some measures that you get as output, like creepages, contact forces, and so on. How do you calculate damage from them? You need to deal a little bit with numerics, because all these simulations, as you will see a little bit later, are iterative. So it can be quite time consuming to do these calculations. So good numerics is also important. When you want to optimize the system, then it's also about optimization. For example, also the vehicle suspension design, you might want to optimize the wheel rail interface management. As I already indicated in the beginning, the geometric interaction between wheel and rail is extremely important. Yeah, and so on. I don't go into the rest of these bullet points there. We have been dealing with this topic for quite a long time, as you can see on this slide. The first thesis that one of our students did on the topic was in 1999, the first wheel wear prediction algorithm, at that time for a freight vehicle. Then several theses updated, extended the work, for example, in Bloom that firstly dealt a little bit with RCF. My colleague Carlos Casanueva worked on switches. Babette Dirks, for the first time in a systematic way, coupled RCF and wear. And then in 2016, we had one thesis that dealt only with contact mechanics, actually developed a non-Hertzian contact theory that is needed for exact prediction of the damage, but that still needed to be numerically efficient to not extend the simulation times too much, even though the contact mechanics are more exact. And then the works which I mainly will talk about today are on one hand from our colleague Syed Hosseiniya, who finished his thesis in 2017, is now a researcher in our group, and Vishak Krishna, who will defend his thesis in fall this year. And as already indicated, the examples I will take up is calculating of rail damage in combination with grinding actions, wheel damage, one short example of a recent master thesis. And then finally, I will talk a little bit, that's not the major part of the presentation, talk a little bit about our recent activities on machine learning. Okay, I will start with the work mainly from Vishak Krishna on calculation of rail damage with taking grinding actions into account. To explain why we are doing this, I show here measurements that are actually from Germany. Rail measurements on a rail cross section over 9 years. And what you can see is the time on the x-axis and the wear volume, the volume that is worn away on the y-axis. And on one hand, of course, you wear away material due to the operation, and that you could show by this arrow. That is the wear you get throughout the years by trains passing that cross section. But you also get a significant amount of wear from the grinding actions. And if you do not take that into account when you calculate the iterative change of rail profile and in turn the interaction between wheel and rail, you miss an important part of what happens with the rail during its life. A first indication that it is probably not the best idea to, in certain intervals, grind the whole line, you can see from the Swedish iron ore line, which is a line in northern Sweden where iron ore is transported from the mines in Kiruna to the harbors, either to the west in Norway or to the east in Sweden. And here you see a part of the line, and you can see we got grinding schedules throughout the years from the infrastructure manager, and until 2008 they just ground the whole line with certain intervals. Then for some years we did not get information. I really don't know actually why, but then you can see in recent years they did not grind the whole lines, but some parts were ground more often, more frequent than other parts. And if you compare it to the to the curvatures, to how the line is built, you can see that the parts with the tighter curves are ground more often nowadays. So from experience, they already introduced a more intelligent grinding scheme than just grinding the whole line. And what we were thinking of is that by using real prediction, perhaps you can make it even smarter and save even more money for the operation. What is then needed to predict the rail surface damage? On one hand, as said, a good vehicle model that includes all data needed, suspension data and so on. You need a lot of track information, the general track layout, you need the track irregularities, and you need the rail profiles, of course, but you also need to know quite a bit about the operation, about possible traction and braking, what are the real speeds on the line, and then environmental influences like friction, which typically we assume stochastically, but you need to know something about the distribution of the friction. And how do we do the simulations then? And this is actually not something that was introduced in the first thesis we had on that topic. With a model you have and the knowledge about the track and the operation, you define a number of operational cases, and then you do the simulations, take out the relevant output data from the wheel-rail contact, and then with the damage model you calculate the wear on wheels and rails. In this case, mainly the rail is interesting. Then you update after a certain time the rail profiles, and then if you already have achieved the tonnage passing you want, then you take out some key damage indicators, for example, like worn off area, change in flange height, flange thickness, things like this. Otherwise, with the updated rail profiles, you go back to the start and do the simulations again, and usually this loop is gone through perhaps about 40 times or so. There is another arrow, as you see. We also calculate the rail surface damage, RCF. I will come a little bit more to that in the second example on the wheel rolling contact fatigue. So that's the basic scheme, but Vishak, our student, added another layer on this. And as I said, from time to time, there's also grinding. The grinding actions are taken, and then after a certain time, you can yourself decide in the simulation after which scheme you want to introduce the grinding. You take away some material due to the grinding action, and in standards you can see how grinding usually is done, how much material you take away and where. And if you then also talk with the people who are doing the grinding, you can get quite a good idea on how this is done. So as shown from the measurements in Germany, also from grinding we take away material. And then we have done calculations. Here we actually also compared two different bogie designs, because that was done partly within an EU project, where and the EU project was called Freight Rail, where a new bogie type, a modified Y25 bogie. Y25 is a very common European freight bogie. Modified bogie was developed, and our task was to investigate how track friendly that new bogie is compared to the standard bogie. Yeah, I already talked about that. You need vehicle design, track operation, and maintenance type. And here on this slide, you can see the results of our calculations. To the left, you will soon see how the wear increases. You can see both the wear from the vehicles passing and also from the grinding action. In the center, you will see how the rolling contact fatigue develops, but then after each grinding, rolling contact fatigue is set back to 0. That is an assumption we make, that the grinding is able to fully remove initiated cracks. And on the right side, you will see how RCF would develop if you would not reset the RCF with a grinding action. So here you can see the results developing. You can see the mega gross tons increasing. We simulate until about 100 or perhaps even exactly 100 mega gross tons. So you see the wear increasing, RCF developing and then ground away. And here how it would look like if you don't reset. And you can see the picture of RCF developing for the two different bogies is a little bit different, because the freight rail bogie on the lower line is a more curve-friendly bogie than the standard freight Y25 bogie. You can see it a bit here also how the different bogies with respect to rolling contact fatigue risk would behave in different curve radii, and especially obvious it becomes, for example, in a 1500 meter radius, where you see that the curve-friendly freight rail bogie would lead to significantly less risk of rolling contact fatigue. And that, for example, could be used to optimize grinding intervals. When you, for example, know you introduce a new type of running gear that is more curve-friendly, then you can calculate how much can I extend the grinding intervals. But you can also use the calculations to see if you have very special weather conditions. For example, you have faced some months where it is extremely dry, or also then you could use this type of calculations to see, do I need to grind a little bit more often now because of the changed operational conditions. So all these things that could happen, or if you want to change the rail profile, you could see how does this influence and how could I change the grinding intervals due to a change of the rail profile. The second example I want to show you is on calculation of wheel damage and the wheel life prediction model that is mainly developed by Said Hossein Nia in our research group. And that is actually done fully on the iron ore line with the iron ore vehicles. And what I am showing today is for the wheels of the iron ore locomotives. This is an operation in northern Sweden and the very north, so it's very cold there in winter, and it's winter for a very long time. They have snow for perhaps 7-8 months during the year and down to -40 during winters. It's 30-ton axle load with, I think, 68 iron ore wagons after this locomotive with 4 3-axle bogies. And from observations that our colleagues from Chalmers and Gothenburg have done on the wheels, you can on one hand see that there are cracks on the locomotive wheels, and on the right hand side here you can see statistics over the probability of the need of reprofiling the wheels after a certain operational distance, a certain running distance. And that's what we would like to be able to redo with help of simulations, because then it could help you to plan the reprofiling needs. If we could say the operator, as a result of our simulations, yeah, after 50,000 kilometers, 3/4 of the wheels need to be reprofiled, then the workshops can do a good maintenance planning there. The logic of how we do the calculation is basically the same. Again, you need a good vehicle model to track information, the operational information, and this time, since it is about the locomotive, you also need to know about the flange lubrication that you have, and we also had to introduce at least a simplified model for the traction control, because that is of course also important for the creepages that arise in the wheel rail contact. So you need to know quite a bit about that also. As said, the simulation is very similar. We need a simulation set, we need the vehicle model, we calculate the wheel rail contact response. With the damage model, we calculate both the wear and the rolling contact fatigue. And then after a certain mileage, we update the profile, and either we say, okay, we are satisfied, we take out the final results, or with the updated profile, we go back and to the beginning and redo the calculation. Here I still want to give you some impression on how we do the damage calculations. Firstly, the contact patch is divided into a number of elements, say about 40 elements for the contact patch. And then each of the elements we check if the yield limit in shear is exceeded. And if it is exceeded, we increase the count, say, then there is the risk of rolling contact fatigue, because if you look into Professor Johnson from Cambridge, his shakedown theory, then it is said if you exceed that yield limit, then there is a risk for rolling contact fatigues. So from that we get such pictures where you can see, depending on the color, how many instances you had where that limit was exceeded, and also where exactly on the wheel those are. But as I said from the beginning, rolling contact fatigue and wear are interlinked. Therefore, we also always calculate the wear. Firstly, we needed to know how the profile changes, because the profile change also influences the contact stresses and the risk for rolling contact fatigue. So you have to do this in parallel, but we also do this to judge how it might influence, or how it will influence, the crack growth. If there's a lot of where we actually reduce the influence of the stresses on crack growth with a certain equation. I don't go into the details here. What is just important, if you have low energy dissipation in the contact, that is an indicator for how much wear you have. You don't modify the RCF calculation. If you have very large energy dissipation, then you say you don't have any rolling contact fatigue in risk at all, because you wear away all initiated cracks, and then there is a linear interpolation between those two zones. And with that, you can get relative information about the RCF risk. With that, for example, you can do parameter studies. Up on the left, we have RCF risk on the wheel profile in normal operation, and what would happen if you do not have any electrodynamic braking on the locomotive, if you change the wheel material, if you would increase the axle load, and so on. These things you could investigate, but you cannot yet get an absolute measure on after how many kilometers running distance would I need to profile. That's only a relative measure. So there's something more needed. So what we can say up to now is how many exceedances of the shakedown limit do we have with respect to running distance, and we can approximate this in a function there. But how do we come to the fatigue life? And there again, we cooperated with our colleagues in Chalmers and Gothenburg. They have done laboratory tests on the rail materials, and they have developed basically Wöhler curves for the material, where you can see, depending on the surface stresses, when the material fails. And with that information, then we can calibrate our results so that we really can also give an absolute measure on when does the wheel fail, when does it need to be reprofiled. And it turned out that we, with quite good quite good agreement, could predict the probability for the need of wheel reprofiling that we got from the statistics from the workshop I showed you in the beginning. This is the measurements. It's just drawn a little bit different. And here you can see the result that we would get from our simulations. So we would also predict, like the statistics from the workshop say, that after about 50,000 kilometers per hour, 3 or 4 axles would need a reprofiling. Here on the next slide, firstly, I show you shortly how it looks like when the wheel profile changes. And down here you can see that we actually again match quite well with measurements of how the wheel profile with respect to running distance develops. And here you can see some parameter studies. Again, like for the rail, also for the wheel, you could predict what would happen if you have a very dry period, how much more wheel reprofiling can you expect so that the workshop is prepared. What would happen if the lubrication on that line, they also have lubrication installed in the infrastructure, and in winter it's not always sure that this is working. So you could also calculate, if they detect that the lubrication has not been working for a while, how would that influence the wear and rolling contact fatigue on the wheels? How much faster would you need to reprofile? And things like this you could forecast with help of this digital twin, with help of these calculations, and help the workshop in the maintenance planning. Okay, one very short example also, that is a quite recent master thesis that we did together with the infrastructure owner. What we have seen already a number of years ago in our simulations is that the rail damage increases with increased gauge. On heavy hull lines, you typically have something that is called gauge widening, that the gauge becomes wider and wider after a while, but that is typically not beneficial for the stress levels that arise in wheel and rail, because you get into contact at parts of the wheel and the rail which are not really thought for contact. You get very small contact patches and very high stresses. So there are regulations on the iron ore line that the track gauge should not be higher than 1450 millimeters. Then they should do something about it. And they wanted our master thesis student to use the digital twin to do calculations and either confirm that operational limit or suggest a different limit. So again, he did simulations according to our iterative damage prediction model. I don't need to go into that again. And then he calculated again the wear and the risk of rolling contact fatigue. And again, some calibration was needed. We knew exactly from informations we had that in one certain curve after 105 days, so much rolling contact fatigue had developed that they needed to do something about the rail. So we calibrated our calculations to that. And then we said, this is the black horizontal line we have there, and everything that is above that value, Trafikverket said that is definitely not okay. So we calculated how does the track gauge influence the time until this rolling contact fatigue arises. And you can see here that it is around 1450 millimeter track gauge that you exceed that value. And also when we did it for a number of curves, different curve radii, you could see that if you are above 1450 with your track gauge, then the RCF risk very steeply increases. So the operational limit that they have chosen, mainly based, I think, on experience, was actually a quite good limit. The figures here on the bottom just show again a comparison on when you look at where on the rail you have the cracks and where we find them in our simulations, that coincided quite well, just to check whether our simulations can be good or not. So not very much left now, because the final part I want to keep quite short. In the last 2-3 years, we started more and more also to use machine learning algorithms, like many people do, for prediction of damage, or not only damage. Applications that we up to now have worked with is detection of track geometry that is out of the limits, local track defects, running instability of a vehicle, or component failure, for example, if a damper is not okay anymore. And for all these effects, we use vehicle reactions. And the idea why I'm presenting it here is, what you can do on one hand is you have a lot of measurements available, and then you can train your algorithms, and when the algorithm is trained, then it can forecast under which conditions the system is not okay anymore. But if you don't have so many measurements available, it's not often so easy to get a lot of measurement results. Then again, you could use the simulation models, the digital twin, to produce a data set that you can use to train your system. And then also, firstly, you can check with your simulations if you can detect the failures. In the end, of course, you need to go out and test it, because you need to be able to detect the failures in real life. You don't win anything if you can detect the failures in your simulation tool. You can just develop the algorithms and train them with your tool. And as said, we have done this for these different types. One study was, for example, to use vehicle reactions to be able to say if the track irregularity is outside the limits, if there's something that needs to be done on the track. And yeah, as said, either you need measurements or you produce the results by simulations. Then you need to extract some features, something which can indicate if there's a problem, and then you can train your system, and then you can use, as in the case for the track irregularities, for example, the standard deviation of bogie acceleration and standard deviation of bogie roll, lateral and roll acceleration, and then you can define a boundary and see, depending on the vehicle reactions of whether the track is okay or not. Again, a master thesis that we had quite recently is on the metro network in Stockholm to try to identify squats by measuring axle box accelerations, and then again training the system to see if you can detect the squats. And one result you can see here, the blue dots are real squats on the line, and the black spikes are indications of squats from the machine learning tool. You can see there are too many indications, but at least the squats that are really existing are detected. Okay, to summarize a bit, the presented tools to a great extent show very good agreement with field observations, and we think that they therefore could be used to optimize either rail grinding or wheel turning intervals with respect to the track section. On one section you need to grind more often than on other sections due to operational changes, as said, very dry periods, for example, the vehicle type, changes of wheel or rail profile, or others. And also our simulation tools could be used to train machine learning algorithms to detect failures in the system. Okay, thank you very much for listening, and I am looking forward to answer, at least try to answer your questions.
Well, thank you very much, Sebastian. We've had one question so far. It's regarding your locomotive wheel wear example. Was the wear different on each wheel or axle, or did they all behave similarly?
You can actually see a difference between the different wheels in a bogie. These were also 3-axle bogies, and you can see a systematic difference if it is the leading, intermediate, or the trailing wheel set. Yes, there is.
Okay. Where do you see the, we have some more questions, hang on. So this is coming from one of our friends from TTC out in Pueblo, Colorado, and he's saying that they had done a similar track gauge experiment and found that rail wear shifted more to the high rail and curves with wider gauge. And they also saw significant shifts in contact position on the rail with RCF. Did you see similar effects?
Yeah, on the iron ore line in northern Sweden, they actually experimented quite a lot with the rail and also with the wheel profiles. But on the rail profiles, for example, they also had quite some problems on the high rail. On the gauge corner, they introduced, for example, profiles in the curves on the high rails with so-called gauge corner relief, where they take away a bit of material in the gauge corner so that you don't get this sharp contact in the gauge corner. So they also had similar problems, and yeah, elaborated quite a lot on that. A lot in the beginning, of course, with trial and error.
Okay, the questions are pouring in now. All right, I'll just take them in order. Is there any research going on related to special track work life? In other words, turnouts and crossings and that sort of thing.
Right now, we don't have so much research on special track elements. We did, as you saw on the timeline, we did some simulations on switches and crossings, but that's not right now our main research direction, I can say. We have done some simulations, but not that much.
Okay. This individual is asking about any papers you may have on your research related to the digital twin.
There are some research papers. We have, for example, one PhD student working on that. So if you want and send me an email, I could put you into contact, for example, with that PhD student if you're interested.
Okay. In the rail grinding work, what depth of metal is assumed to be removed during each grinding?
Oh, that is a good question. Vishak, my PhD student, could directly answer that. But to be honest, I don't remember. He has studied standards and practice quite a lot, but I'm sorry, I don't remember. And before saying something that is wrong, I don't remember.
Well, here's a suggestion. Maybe the people that are sending these emails or questions, we can forward them to you and you can correspond with them. Next question is regarding the wheel reprofiling. Where did you get the data to do wheel reprofile probability?
That was statistics from the iron ore company that owns their vehicles. They, from experience, they regularly take in the vehicles for observation and test or look at how severe the cracks are. Then they have a guidebook, so to say, that tells them how severe the cracks need to be to trigger reprofiling action, and then they put all this into their computers, and then they can get a statistic, see how many percent, how many wheel sets were reprofiled after which running distance, because they also know the running distance of all the vehicles, so that they have these statistics, luckily.
Okay. Can you provide more detail about the method used to determine the RCF damage accumulation? You mentioned that you used the curves developed in a partnership with Chalmers, but this individual would like to hear more about the lab tests.
Yeah, the lab tests were done at Chalmers. I can go. Where was it here? Soon. Here, since they were done at Chalmers, we haven't done it in our lab, so I don't know all the details. But what they tested is, you can see here the FI surf that is an index that also Chalmers developed as an indicator for the risk of rolling contact fatigue. That is also based on the shakedown theory. It's basically like we did, as soon as you are on the right-hand side of the shakedown limit, then there is a risk for rolling contact fatigue, and they, depending on how many exceedances they have, they test it when the material fails, and that's basically the curves you can see here. As I said, it's basically Wöhler curves with a number of cycles, and then when you see the failure of the material. That's the best I can explain right now, I think. You have here a paper given on that site where they talk about how they derive these curves.
Okay, next question is, do you have some work about metric track gauge influence on RCF?
No, up to now we have done all our calculations on 1435 millimeter gauge.
Okay.
But that would of course, with a simulation, it's of course easy to do this, but we haven't done it.
Another question is, this individual's interested in the gauge spreading question. Is there an optimal gauge function as a function of radius?
Yeah, I think I can't tell it so detailed. We could probably, with this results we had, we could say as a function, as you ask, as a function of radius, which would be the optimal gauge. I could imagine that it would be difficult to have such a detailed regulation. It would of course be perfect, but it could be quite difficult to follow up to really get the guys who are doing the maintenance to see what curve do I have now and what is the optimal gauge in that curve. That could also be a problem, I could imagine. So yeah, we haven't looked at it. It would be possible to do it. It's a good idea, but might be difficult to really live up to such a rule, I could imagine.
Okay. And I'll put you in, this individual is actually, I think, somebody you know, and I'll put you two in contact. Have you investigated the effect of various types between wheel and rail, and the effect, for example, of a hard wheel steel on rail wheel wear?
We have investigated that a little bit, but that is actually an area where we ourselves feel that there is even more research needed, because if you look at the shakedown theory, which is used by us and many other research teams to judge the damage, there are not that many material parameters in that. There's the hardness, but that's basically all. And then of course the shear stress limit, the yield limit, but there are not so many parameters that you really can make a good judgment on how different materials influence it. As said, some parameters are there, so we have done some studies, but I think there is more research needed actually in that area to include more material parameters in such damage calculations.
Okay. Next question is, at what point does a multi-body dynamics model become a digital twin? Does it have to include machine learning or other specific features?
And that is also a good question. And one answer to that is that digital twin is just a very modern term that is used, and you are free to, I don't think there is a good definition on when such a model can be called a digital twin. It's partly also in many other areas, engineers are today talking about digital twins. So a little bit it's from our side also that, also in mechanical engineering, this type of models that are used are basically digital twins, because you try to model the reality in the best way, and you can predict what happens in reality with help of a model. So I think basically that's the definition of a digital twin. Also railway operation today, you often talk about digital twins that simulate the operation of railways, for example, delays and things like this. So therefore we started to talk about digital twins also for our prediction models.
I should mention that you're being thanked for unmasking digital twins.
I thought I want to be honest.
Next question is, it appears that much of the benefit of this method relies on an excellent understanding, a model of the behavior of a specific rail vehicle. Are there good ways to extend the benefits to railroads where equipment is extremely varied in its age and design, such as in the US rail fleet?
Yeah, I think that is one of the advantages with simulation tools. It is very easy to simulate each type of operation, even with very bad track conditions. Of course, I think some validation would be needed first to first have an impression of whether it really works. But we have used the tools for quite different types of operation, from high-speed trains in China to freight operation in Sweden, and also we had a master thesis on tram traffic. So I think that with some calibration and validation first, they are applicable for most types of railway operation, actually.
Okay. Do European countries true freight wheels? If so, what's the average interval, and how many intervals can a wheel get in a lifetime?
Yeah, that varies a lot, and the 50,000 that I showed here for the iron ore line, that is very special. The iron ore traffic is a very special type of traffic for European conditions. Don't cite me on that, but perhaps 100, 150,000 in freight traffic, perhaps between reprofiling is reasonable, or even 200,000 running distance, and then perhaps you can reprofile 3-4 times before you have to change the wheels. But that will differ a lot if you look at different types of operations in Europe.
Okay, well, I think that's the end of the questions. And again, I want to, and what I think we'll do is we'll also share the questions and the identity of the people asking them with you via email, and then, you know, if there's further correspondence, it's between, you know, you and the questioner can certainly pursue that.
Yeah, and I can also direct them to the guys who have really done the work, so then you can continue the discussions with the students that really are into it in detail.
Right. With that, I think we can then conclude the seminar, and I want to thank you very much, Sebastian, for a fascinating seminar on a very important topic, and wish you a very good evening. If you haven't had dinner yet, hopefully you can go and join your family for dinner and have a wonderful weekend as well.
Thank you. The same for you then soon in some hours. And once again, thank you for inviting me. Was a real pleasure, even though it would have been nice to be at your university also and really see the people.
Now, next spring. We'll come back next spring, and we've got to get back to Stockholm one of these days as well. So with everything hopefully improving now, that hopefully will be possible. So, well, with that, I'll suggest that we conclude. And again, my best regards to your family and colleagues at KTH. Thank you very much.
Best regards to all of you there at UIUC and everyone else also. Thank you.
Bye-bye.
Bye-bye.